students, we'll study today gravitation. Here in the lecture 1, we will discuss the gravitation, and already this term, you are very much familiar to this term. And next we will discuss the universal law of gravitation. So Sir Isaac Newton, he has invented this law, and also here we will discuss this thing. Now the gravity and gravitation. So gravitational force, here we'll discuss an universal law of gravitation. So before going to the main context, we are just describing here what is the gravity. I'm just taking the pointer. Here, the gravity, this term is very important, and already you are familiar. Now in this lecture, just I will discuss in terms of the physics, right? So gravity is the force occurring between an object and the very big object R. So gravity means, here you can see that there is a ball and it will fall that towards the ground. So gravity means the force of attraction of the earth, force of attraction of the earth towards any object that you have on the surface of the earth. Okay, so it is universal force of attraction acting between all matters. And gravitation, this gravitation is the acting force between two bodies. Suppose I have here one body having the mass m1, another body or object having the mass m2. So in between these two objects, I have some attraction force, right? So some force will be acting in between these two bodies. And these two bodies, whatever the attraction force or the acting force we have, that is called the gravitation. So always remember one thing, there is a little bit difference between the gravity and the gravitation. Gravity means whatever the force in between the earth and your any object. It may be the ball, it may be the apple, it may be any object, right? But gravitation means if you have two objects, suppose two balls, or if you have suppose one bat, one ball, at that time, whatever the acting force between two bodies, that is the gravitation. As I have told that Sir Isaac Newton and Albert Einstein dominate the development of the gravitational theory. Now, the gravity, it is measured by the acceleration that it gives to freely falling objects. Now, what do you mean by freely falling object? Suppose this is the height and this is the ground, okay? And some object you have in this height and it will fall towards the ground. So there will be no force acting on this unless only one force you have, that is the gravity, that is the force due to the earth. Okay, so gravity, that is measured by the acceleration that gives to freely falling object. Freely falling object means you are not applying any other force to this object, but it is freely falling to the ground, right? So this is the gravity will be measured in terms of the acceleration with which this object will fall to the ground, okay? And Earth's surface, the acceleration of gravity, it is denoted by small g, and it is 9.8 meter per second square. Sometimes in your numerical, you can see that they are giving g that equals to 10 meter per second square, right? Thus, for every second an object is in free fall, its speed increases by about 9.8 meter per second. So for every second, its speed that increases by how much? That is 9.8 meter per second. Okay. this much is the gravity. Now, here you can see that one experiment or one game always we are doing in our childhood, that one stone we have, suppose, just a minute, we have suppose one stone here, and we are binding this stone with the thread, and suppose you are this person, and here you are the person. So with a thread in your hand, you are just moving it in this circular motion. Okay, in this circular motion you are just moving the stone. There was a game. Okay, so before the thread is released, the stone moves in a circular path because you are holding it and you are applying the force. So with a certain speed, and it will change the direction obviously. First the direction is this one, then this one, then this one. So always it is changing the direction, and whenever it will maintain some certain speed at every point, the change in direction that involves the change in velocity and acceleration, right? So the force that causes this acceleration and keeps the body moving on this orbit, or that moving with this circular path, and this is called centripetal force. Here in this figure you can see this is an object, and this is the center of the circle, and in this circular path this object is moving. So whatever the velocity that has been denoted by this arrow, and it is denoted by v velocity, but there is another force that is acting on this radius, that is called the centripetal force. And due to this centripetal force, the ball is not moving away from the circular path. So if we do not have this centripetal force, then you can see that this stone that flies off along a straight line. You can see at that time, if you do not have any centripetal force, this stone that will move along a straight path. Okay, straight line. So this straight line will be the tangent to the circular path. So that means this gravity means everything, every object in our earth that will be attracted by the earth with the force. And you can see using this experiment that just you take one stone and bind it stone with the thread, and you just hold the other end of the thread and you just move it in the circular motion. So you can see that it will just move always in the circular path. It will follow the circular path. But after certain time, if you just skip, if you are not giving the centripetal force, if you are not have the centripetal force, at that time you can see that it will that stone flies off. Okay. Now gravitational force. Here you can see Earth, Moon, Mars, Venus, everything is moving. But the motion of the moon around the earth you can see in this figure, right? And Mars, Venus, all those planets, it has the movement with the centripetal force. But here at the center, what you have, that is the sun. So here you have, just a minute, here you have the centripetal. Here you can see that this is the sun. This is the sun, okay? And here you have, suppose, Venus. Then you have some Mars. So all this will move here. All this will move here. But there is some centripetal force. There is some centripetal force here. So that's why all the planets, that they will move around the sun. Similarly, the moon here, the moon also, it is just moving around that is earth. Okay. So if there is no such force, you can see that the moon also, that will move in a straight line motion. Okay. Not circular path it will follow. Now gravitational force, this is very familiar picture. Apple is falling, and this question arises in the mind of Sir Isaac Newton. It is seen that the falling apple is attracted towards the earth. Okay, fine. He has invented all those things, but why does apple will be attracted by the earth? But one question that is, we do not see the earth moving towards the apple. Why? Because here you can see that this answer actually it has been written here. I'm just explaining this one. This is the apple, and the mass is very, very small. And this is the earth. Mass is very large. So according to third law of motion, the apple also attracts the earth. But according to second law of motion, the acceleration that is inversely proportional to the mass of the object. Inversely proportional to the mass of the object. Yeah, okay. So if inversely proportional to the mass of the object, that means if mass is of an apple is negligible small compared to the earth, so we do not see the earth moving towards the apple. The earth moving towards the apple. Okay. If you have one apple that has a very large, very, very high mass, at that time it might be you can see some force, but here actually it will not attract because very negligible mass you have in the apple. Okay. So this is Newton's law of gravity. So with these events, Newton concluded that not only does the earth attract an apple, the moon, but all objects in this universe attract each other. And this force of attraction between objects is called gravitational force. That means if I have earth here and I have moon that is moving around this, so this will also attract this earth. The earth will also attract this moon, also the moon will attract this earth. Like that, any two objects in this universe always attract each other. Always attract each other. Okay, this has been concluded by Sir Isaac Newton. Now he calculated so the circular orbital motion here, that in the orbital motion what will be the inward acceleration? This acceleration will be 4 pi square r by t square. So I am drawing here. Suppose this is the r. Okay. And this one is your earth, and around this just a minute, okay, again I have to take point pen. Okay, so this is the moon, okay, and this is the moon. Sweet moon. So here the radius, whatever you have in the orbital motion, the radius of the orbit, that is the capital R. Okay, that is the R. So R, that is what? That is the radius of orbit. Radius of orbit, and this orbit is circular, and the t, that is the period, time period. Okay, that is the time period, and this equation is applicable for the earth while it is just moving around the sun. That means any two planets also, or sun, or in between sun and earth also, you can see this thing. And t is the time period. So the acceleration, this is the inward acceleration. So I can write here inward acceleration. Inward acceleration, that is a. Okay, inward acceleration, that is a, that equals to 4 pi square r by t square. Okay, Now, as I have told you in this lecture, I will discuss also the universal law of gravitation and Newton's law of gravity. Here, you can see two masses you have, two objects you have. One has the mass m1, another has the mass m2. So, whatever the force between these two mass m1 and m2, that will be our gm1. The force between these two will be g m1 m2 divided by d, where d is the distance between these two objects and g is the gravitational constant. Here you can see that a body of mass m that will experience a force and accelerates with the f by m. This will be discussed later on. So if I have m1 and m2, let this is m1, let this is m2, and in between these two, I have the force F12, where F12 is the magnitude of gravitational force acting between M1 and M2. And R12, this is the distance between M1 and M2. So the force equals to G M1 M2 divided by R12, where G is the universal constant. And G is nothing but 6.673 into 10 to the power minus 11 Newton meter square per kg square. So this is Newton meter square per kg square. Okay, 6.673. Actually, it is 6.67259. So by approximation, I can write 6.673 into 10 to the power minus 11 Newton meter square per kg square. Remember this equation because numericals will come while you have to use this equation. So F12, that is G M1 M2 divided by R12 square. R12 square. Okay. So what is the importance of universal law of gravitation? The universal law of gravitation, that using this we can explain a lot of theory. First, the force that binds us to the earth, that we can define or we can explain using this universal law of gravitation. The motion of the moon around the earth, just now we have described that thing. The motion of the planet around the sun, you have seen one figure where moon, Venus, Mars, everything we have seen. The tides due to the moon and the sun. This also we'll discuss later on. The last bit. Now the tides. You have heard this term, and some of you, I think you have seen the tides also. Who have the house very near to, or who have just have seen some sea tide, or also tides in a river also, very big river also. You can see the high tide or low tides. And high and low tides, these are caused by moon. The moon's gravitational pull generates something called tidal force. Okay. So here you have the earth. You have the earth. And here you have the moon. Okay. You have the moon. So here you can see that the moon's gravitational pull that generates something that is called tidal force. As I have told you, if earth will give some force to the moon will also give some force to the earth, right? So that means the moon's gravitation, there will be some gravitational force of the moon. So this pull the earth. Okay. So the tidal, and it is called the tidal force. It is called the tidal force. So the tidal force causes earth and its water to bulge out on the side closest to the moon. And the other side that is farthest from the moon, that has no bulge. So these bulges of water are high tides. So what you can see, suppose this is the position and this moon. So this part of the earth very close to the moon, So this moon will pull this moon will pull the water of the water bodies of this side, and this bulge in the water body, that is called the high tide. Okay, so in this next, you can see here in this figure, this is the moon and this is the earth, and in this earth you can see that the earth always it will rotate along its axis, right? That means what? Some of the portion of the earth will come in front of the moon, okay, near to the moon. Oh, but better I have to use the term near to the moon, and some of the portion that will be far away from the moon. So which portion of the earth that is very near to the moon, that portion, in that portion the tidal force that will be acting. And when this tidal force will be acting, that means you can see that in that portion, whatever the water bodies you have, those water bodies will bulge out. And here, at that time, there will be some high tide. But at the same time, the opposite side, you have low tides. Okay, so this cycle of two high tides and two low tides occurs most days on most of the coastline of the world. Okay, so when this is the main reason of the tides. So tides are really all about gravity. When we are talking about daily tides, it's moon's gravity that's causing them. Already I have discussed how the moon's gravitational force or pull that causes the bulge in the water bodies. So at that time the water wants to bulge in the direction of the moon, and due to this tidal force you can see that the bulge the bulge of the water at that is called the high tide. This bulge is what we call the high tide, and earth rotates always. That means if you have in one side high tide, in other side you have low tide. Okay. Now, does anything else affect tides? Okay. Yes, the sun also causes tides, just like moon does. Here you can see that this is the position. This one is your earth, moon, and this is the sun. So the sun also causes tides, just like the moon. When the earth, moon, and sun line up, you have in one line here, which happens at times of full moon or new moon. The lunar or the solar tides reinforce each other. And here, extreme tides will occur, that is called spring tides. When lunar and solar tides act against each other, the result is unusually very small tides. At that time, it is called neap tides. Okay, so here you have to remember one thing: neap tides, and here you have, that is the spring tides. Okay, so whenever the lunar and solar tides reinforce each other, then there will be a tide. At that time it is called spring tides, and when you have lunar and solar tides against each other, at that time there will be neap tides. So that means yes, the sun also affects the tides. So here, let's solve this numerical. Okay. Always I have told you, whatever the given data, you have to first write down all these data. Now determine the gravitational force if two masses are 30 kg and 50 kilograms separated by a distance 4 meters. Fine. So mass, let it be M1, that is 30 kg, M2 50 kg, distance D 4 meter, G has been given 6.67259 into 10 to the power minus 11 Newton meter square per kg square. So we know that the force, gravitational force, what we have to find out, the gravitational force, and this nothing but G m1 m2 divided by d square. So if we put all the values, then we can find out 6.67259 into 10 to the power minus 11. M1 is 30 kg, M2 is 50 kg, and distance is 4 meter, so 4 square, and you will get 62.55 into 10 to the power minus 11 Newton. Okay, fine, got it? Next, the mass of the earth. Okay, earth is very big, so let mass of earth that equals to 6 into 10 to the power 24 kg, and here let denote by capital M, and mass of moon that equals to 7.4 into 10 to the power 22 kg. Let define it small m. If the distance between the earth and the moon is 3.84 into 10 to the power 5, 3.84 into 10 to the power 5. So I don't know why it is coming. Okay. So here distance, let it be d, and this equals to 3.84 into 10 to the power 5 kilometer. So here first we are trying to find out the distance in meter. So 10 to the power 3 meter, that means 3.84 into 10 to the power 8 meter. Fine. And we have to find out here another thing has been given G, that is 6.7 into 10 to the power minus 11 Newton meter square per kg square. Okay. And we have to find out the force. So the force that equals to G m divided by d square. So if we substitute all the values, 6.7 into 10 to the power minus 11, and this is 6 into 10 to the power 24, and mass of the moon 7.4 into 10 to the power 22, this whole divided by d 3.84 into 10 to the power 8 whole square. So it will come 2.01 into 10 to the power 20 Newton. 2.01 into 10 to the power 20 Newton. And this is the answer. Okay. Thank you.